is, I think, in our usual classroom format, right? So, Sajjad,
Which one?
they changed it. I
Is
think.
it?
Yeah, because now all of us are participants, which we requested.
No, 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 no.
I mean, currently there are 0 attendees.
Yeah.
There is a category
All
called
the
attendees.
panelists. Yeah.
Oh, okay.
They did not change. Yeah. So we should wait, I think.
Yeah, there is some. Five, six.
I don't understand why they put all the attendees separate group. I don't understand.
Right. Only one.
This they told that is the webinar format. It's like two different.
Hey, so how is Rohit doing, by the way?
Rohit is doing good. He
In IIT somewhere,
in,
right? Palakkad.
yeah, Palakkad.
Right. Okay. Still talk to him? I'm sure you must be there.
Yeah, we are in touch. Every week.
He's Indian bill.
Maybe suggest can we write that because there are not too many attendees.
No. So see, they will be able to join after 2 o'clock. So I don't think so. They will be able to join before that. So I see one people join before that.
Yeah, that means they can join. So is Manish here? So Manish, should I announce now?
Yes.
Yes.
Yeah, you can announce now.
Yeah. So now I think they can join. I see 2 people join. Yeah.
Yeah, so good afternoon, everyone. So there is one small announcement. For all the participants, so if you want to ask any question, please click the button, raise your hand, and you will be immediately unmuted and you can ask your question. And there is also chat option. If you ask your question, write down your question there, we can immediately communicate. We will immediately communicate them.
So Surat, shall I share my screen just to make sure?
Yes, please share your screen. I think you can share. You are also.
I can share. Yeah, I am seeing this. Can you see?
Yeah,
Yes.
I can see.
Okay.
I hope everyone can see.
Yeah, we can see that.
Yes, I can see this.
So now it is 2. So shall we start the session?
Wait one more, I think 1 more
You
minute.
can wait a few more minutes, just for a few more to
Yeah,
turn
yeah,
a couple of
yeah,
lights. So Seshadri, start.
Yeah, I think.
You can start, I think.
Yeah.
So, all right. So okay. Welcome back to everyone for the afternoon session of this conference. We had a bit of analytic number theory in the morning, so now we're ready to look at some algebraic aspects of number theory, starting with Dr. Krishna Hanumantu from CMI. As you see, the topic is the title of the talk is Seshadri constants. Yeah.
Okay, thank you. Let me start by thanking the organizers for inviting me here. It's a great pleasure for me to be here. I'm somewhat apprehensive about this. The title of the conference is Conference on Number Theory. And related topics. I'll go for the related topics here. So this will be mainly in algebraic geometry. The topic of Seshadri constants does have interesting connections to number theory, but unfortunately, I will not be able to stress this a lot, but hopefully you'll see some useful things here. So also, I'm not sure whether everything I'm saying will be clear. So please do feel free to stop and ask me questions or chat if at any point, if there are any questions, I'll be happy to stop and explain. So let me start with this basic setup for me. So X will be a smooth projective variety over, I mean, I can do this over arbitrary fields or arbitrary algebraically closed fields, but because this is supposed to be a preliminary talk, I will stick to complex numbers, something that we are all familiar with. And if you are not completely, I mean, this is something that you need not be very familiar with this, but think, for example, the complex projective space. Okay, so think of this because most of the or several of the things that I want to discuss today will be for Pn, in fact, just for P2. Okay, so think of this and let L be an F line bundle. Okay, so it is a line bundle which is Nef. So that means L dot C is greater than or equal to 0 for all curves in the surface. Okay, so we want the line bundle to intersect every curve, the usual intersection product, non-negatively at every point. Okay, and we are going to take a bunch of points, finitely many points in X. So R is a positive integer, of course, and you take R points. So then I'll just right away define the Seshadri constant, and then we'll discuss its properties. So the Seshadri constant of L at these points. So that's the terminology. And it is denoted usually by this. So you are highlighting this variety, the line bundle, and the points. Okay. And typically when you have the variety clear from the context, you omit that from the notation. So you have this is equal to, so I'm going to write the definition. The whole talk really is introducing this object, and we will look at examples, properties, and applications, and main questions on this. So what we do is we look at infimum of a bunch of rational numbers. Okay, so we look at L dot C is the intersection number, so that's an integer. We look at multiplicity of the curve at each of the point, add them. So this is a rational number, and infimum over all curves C containing, so you want the denominator to be a positive number, obviously, containing at least one of the xi's. Okay, so I hope the definition is clear. I will do an example right away, but we simply look at ratios like this, L dot C divided by this. So now on an arbitrary variety, these are a bit more complicated, but for projective space, this is relatively easy to compute. Okay, so let me right away, before I discuss more properties, look at some basic examples so that if you have not seen this before, you can, this is more comfortable to you after these examples, hopefully. So I'm going to stick to the surface. Most of the talk will be on surfaces. A lot of work on algebra, Seshadri constants is really in the case of algebraic surfaces. And I'll take on P2, we know, of course, the line bundles are, the group of line bundles under tensor product is isomorphic to the integers generated by this O1, the hyperplane bundle. Okay, and now if we look at some properties. So for example, some cases. So if you take R equal to 1, so remember R is the number of points. So R is the number of points. And in this example, I'm taking R to be 1. So what would this be? So I'm going to simply write like this. Simply, I'll omit P2 from the notation because everything is on projective plane. So what would this be? So this is by definition infimum of ratios like this. You take L dot C, so X is P2, so I'll write P2 here. L dot C divided by multiplicity C at X. So now these are curves in P2. So now curves in P2 are easy to understand, right? They're given by homogeneous forms in 3 variables of a certain degree. And L dot C is actually nothing but the degree. So in this case, L dot C is actually the degree of the curve, right? If you take O1 dot a conic, for example, this will be 2. L dot C will be 2 in that case. L being O1 is important. And multiplicity is simply, it's a measure of singularity. I mean, that I haven't mentioned here. In general, you can define multiplicity of any curve at a point. In the case of plane curves, as in this example, things become very easy. So you look at the polynomial, dehomogenize it with respect to the point, and then you look at the least degree term. Okay, the degree of the least degree term, that's the multiplicity. So now what are we going to look for? We are looking for L dot C divided by multiplicity C at X. So we want to look at all curves through our given point. So here X is arbitrary. We will see in a minute that X doesn't play a role here. Any X will give the same answer. So the whole point is to look at curves through the point. So what are curves? to a point X. So what are the curves through a point in the projective plane? So of course we can take lines. Lines of course means degree 1 curves. Okay, lines are obviously non-singular. So the Seshadri ratio. So this is typically called, just for convenience, Seshadri ratio. So Seshadri constant is the infimum of Seshadri ratios, and every curve contributes one Seshadri ratio. So you look at all curves and take the infimum to get Seshadri constant. So this is the Seshadri constant. These are Seshadri ratios. Okay. So what is the Seshadri ratio coming from a degree 1 curve? The Seshadri ratio, I'll simply write it like this, SR. So this is SR is simply degree by multiplicity, right? And degree is 1, multiplicity is also 1 because it's a smooth point. So Seshadri ratio is 1. What about conics if you take? That means you take degree 2 curves. So remember, the degree 2 curve must pass through the point. So what is the Seshadri ratio? Degree divided by multiplicity. So 2 divided by, now this is unlike in the line case here. So sorry. I'm stuck here. Okay, sorry. So unlike in the line, in this case, every line is smooth. So the denominator will be 1, right? Whereas there are potentially singular conics. So the denominator can be bigger than 1. But what is a singular conic? This is something that we learn in basic, a course in plane curves. Only singular conic is this. It's a union of 2 lines, right? And in this case, the multiplicity will be here. Multiplicity is 2. Correct? So a conic cannot have a multiplicity 3, 4, 5 point. So multiplicity, so hence is always less than or equal to 2. Of course, if it's a singular point, multiplicity is 2. If it's a smooth point, multiplicity is 1. It cannot be any other number. So the degree divided by multiplicity is less than or equal to 2 by 2. So it is either 2 or 1. So in either case, this is 1. And remember, we are interested in the infimum. So the 2 by 1 case is not relevant for us because we already know that 1 is the Seshadri ratio. And now you can see the pattern in general. So if you take a degree D curve, C, and if X is in C, so in this case, the basic fact is multiplicity of C at X is less than or equal to D. Now this is a simple algebraic fact. If you take a degree D curve in P2 and a point on that curve, multiplicity cannot be more than D. And it is exactly D precisely in this kind of situation. So except in this very trivial case of union of D lines, multiplicity is in fact even strictly smaller than D. So what is the Seshadri ratio? We know that Seshadri ratio is less than or equal to degree. Of course, it is degree C divided by multiplicity. And this is less than or equal to D. Less than or equal to D by D, I should write. So every Seshadri ratio, sorry, all Seshadri ratios are less than or equal to 1. And, okay, so that's not correct. So what I want to say is that hence infimum of L dot C divided by multiplicity C at X is 1. So I think there is a mistake here. So I'm sorry. So I should really put greater than or equal to 1 here, right? Because this can be 2 by 1. So 2 by 1 is greater than 2, 2 by 2, and similarly here is greater than or equal to 1. So basically what I said is because all Seshadri ratio are greater than or equal to 1 and one Seshadri ratio is equal to 1. So this is the conclusion of that. I mean, I wanted to do this in complete detail so that it's clear to you. So all Seshadri ratios are at least 1. One Seshadri ratio, for example, this one is exactly equal to 1 because through any point in P2 there is a line. So one Seshadri ratio is equal to 1. All Seshadri ratio are greater than or equal to 1. So we have Seshadri constant is 1. So is this clear? So please feel free to, I mean, this is the most, it's like a simplest possible computation of Seshadri constant. But I wanted to do this in detail so that you are comfortable with the definition. Okay, now let me quickly go through the more interesting cases. So if you take 2 points, and now you start to see some interesting geometry here. So if you take 2 points in the projective plane, what is the Seshadri constant? L is as before O1. Okay, so here we take infimum of curves which contain at least one of the points. Right? So you look at all curves which contain at least one point. You need not contain both of them. And then you look at these ratios, and you look at the infimum of that. So what are some of the Seshadri ratios? So if you take a line through 2 points, so if you know in the projective plane, given any 2 points, there's a line. So this is L, let's call it small l. So then what is the Seshadri ratio for L? It is degree of L divided by 1 plus 1. Because the line has multiplicity 1 at x1 and multiplicity 1 at x2. So this is 1 by 2. So Seshadri ratio for L is 1 by 2. Now, if C is any other curve, such that xi is in C for some I. So either x1 is in C, x2 is in C. Of course, both of them can also be C. Then this is now we're going to use a little more geometry. So then if you apply Bézout's theorem, what does it say? If C is a line, C is, okay, so I'm going to assume also that, assume L is not a component of, for now, of C. Okay, so that I can apply Bézout's theorem. So L is not a component of C. So then what we have is C dot L is greater than or equal to the sum of multiplicity C at x1 times multiplicity L at xi. Okay, so from I equal to 1 to 2. But this number, because multiplicity of L at xi is exactly 1, this is exactly this. So this C dot L is greater than or equal to this. But what is C dot L? The intersection number on the plane, projective plane, has a property that C dot L is just degree of C. So degree of C is at least this much. So hence Seshadri ratio for C is equal to degree C divided by sum of the multiplicity, and that's greater than or equal to 1. Okay, so what do we have here? So we have, so all, okay, so one Seshadri ratio is equal to 1 by 2. And okay, I don't quite have that all other Seshadri ratios are at least 1 by 2. All I can say is that if C doesn't contain L, then SR for C is greater than or equal to 1. Okay, now I'll make a general remark here, which is a simple calculation in algebra, really nothing more, is that Seshadri constant that I defined earlier. Okay, so this is a fact. Let me not call it a remark. a fact is that this is actually equal to L dot C divided by the same Seshadri ratio, but instead of taking all curves, we take all irreducible curves. So we put this condition irreducible. Okay, so the infimum does not change. If you put reducible curves, so irreducible curves. So basically what I'm saying is that it suffices to take in the definition of Seshadri constant. So, and if you assume that C is irreducible in this example, then of course it does not contain L. All you need to do is C is not equal to L. So if C is irreducible and C is not equal to L. So any irreducible curve that is different from L cannot contain L. So then Seshadri ratio is at least 1. So hence, so the conclusion is Seshadri constant of L at 2 points is 1 by 2, because 1 by 2 is achieved and every other irreducible curve gives at least 1. Okay, so that's the Seshadri constant for 2 points. Now I'll do one more example and then we will move on. In the first 2 cases, whether you take which point you take or which pair of points you take didn't matter, because you get 1 by 2 always for 2 points. Here now they matter. So we have 2 cases. So x1, x2, x3 are collinear. So that means there is a line containing all all of them. So then Seshadri ratio for L is equal to degree by sum of the multiplicities, which is 3, because all 3 points are on the line. And one can check. So one can check using Bezu as above. That all other Seshadri ratios are greater than or equal to 1 by 2. Okay. So
Krishna, in the last example, last example, don't you need it is greater than or equals to half, and
it is even greater than or equal to 1. So it is certainly greater than or equal to half.
And there exists.
Yeah, there is one, because the line through them gives 1/2. So one Seshadri ratio is 1 by 2, right?
You said it is exactly half.
Yes. Because you take a line through the 2 points. The Seshadri ratio contributed by this line is exactly 1 by 2.
There is one.
Yeah.
Okay.
Yeah. And every other thing is in fact even greater than or equal to 1. So certainly greater than 1 by 2, right? So now coming back to 3 collinear points, you have this condition. Okay. So this is the first case. So if the points are collinear, you get 1 by 3. If the points are non-collinear, that means they don't lie on a single line. Then okay, so this is something that I'm obviously spent too much time so far. So I will just assert this. This one can check. This is not difficult to check. So you have 3 points. You can take a line through 2 of them. By hypothesis, the third point is not going to be on that line. So the Seshadri ratio here will be 1 by 2. Okay. So, and nothing else will give less than 1 by 2. So it will be 1 by 2. So here I want to remark that. So now you have for triples of points, different values of Seshadri constants, depending on the position of the points. So for a general, okay, so remove this, 3 points, Seshadri constant is 1 by 2. For special, Seshadri constant is 1 by 3. Now, this is a general phenomenon that if you take, so clearly being collinear is a special condition, right? Said in a different way, if you randomly pick 3 points in the projective plane, they will be non-collinear. So this is a closed condition. So general 3 points, Seshadri constant is bigger than special points. Okay, so the most interesting case is we look at general points. So Nagata actually sort of systematically studied this, and this is not difficult to show. For general points x1 through xr, where r is less than or equal to 9, the Seshadri constant is given by, for 9 points or less, as we just saw, it is 1 for r equal to 1. It is 1 by 2 for r equal to 2, 3, and 4. And it is 2 by 5 for r equal to 5. So as soon as you have 5 points, you can think of the conic through 5 points. So the degree 2 divided by 5. Okay, and you can check using Bayes' theorem that nothing smaller than 2 by 5 can occur. Okay, and these are also not difficult. You have also 2 by 5 for 6 points. You have 3 by 8 for 7 points, 6 by 17 for 8 points, and 1 by 3 for 9 points. So these are. Okay, so this is just, I mean, these are not difficult. Nagata, I mean, this is not what Nagata mainly did, but he systematically studied them and exhibited curves which attain these values here. For in these cases, it's clear. In these cases, you have to be a bit clever in computing, finding out which curves achieve this. Okay. So now the question is, what happens for when r is greater than 9? And this is related to the celebrated Nagata conjecture, and which I will spend some time discussing. In the same paper where he, or in the same sequence of papers that he Nagata wrote in late 50s, studying these things, he discussed this. And this is actually the main, studying plane curves and interpolation problems on plane curves was not his primary concern. His primary concern was a counterexample to Hilbert's 14th problem. So Nagata conjecture arose out of Nagata's counterexample to Hilbert's 14th problem. Okay, so let me spend a few minutes stating this. So Hilbert's 14th problem has several versions, and in particular the original one which Hilbert stated, but Nagata sort of generalized this. Nagata called this, the current version that I'm now going to write, the original Hilbert's 14th problem is what Nagata called this. So let K be any field, and let's take the polynomial ring over K in n variables. Okay, so you take the polynomial ring in n variables, and let's take G to be a subgroup of the general linear group. Okay, any subgroup. So then, of course, through the standard permutation of the variables, so G acts, or not permutation, but by any matrix acts on the variables here. So a subgroup of G acts on R. Any polynomial inherits an action of G. So let the fixed subring to be A. So this is R power G. So these are all polynomials which are fixed by every element of G. So this is the fixed ring. Then the question is A a finitely generated K algebra? So this is a subring of the polynomial ring. Is it a finitely generated K algebra? So now this is the problem that Hilbert stated, and one can check this is answer is yes. If, for example, G is a finite group, or more, this is something that was known, but more generally if G is what is called a reductive group. Okay, but Nagata was the first mathematician who said that the answer is no. In general, answer is no. Okay, in general, answer is no. First example by so I should also mention that Zariski is an important name in this thing. So Zariski actually also, I mean, I should mention this. So Zariski proved that answer is yes if n is the number of variables here, if n is 1 or 2. And this is important because Zariski connected this to a question in algebraic geometry. He interpreted this ring, invariant subring, as a section ring of a divisor on an algebraic variety. And then the question of finite generation of A is translated to question of finite generation of section rings, which is an important question. I mean, it has celebrated history in algebraic geometry. So that was Zariski's contribution. Nagata carried this forward in computing, in giving his counterexample. So what Nagata did, I cannot the details, but I'll just want to set up what Nagata did. So what Nagata did was he looked at R. So he looked at this particular polynomial ring in 32 variables. I'm not going to describe the action, but if you want to describe the action, this grouping these variables like this becomes important. And he took G to be the 13-fold direct sum of the unipotent group. So GA is actually nothing but this as additive groups. Okay, so Nagata did this very ingenious thing. So this is the most brilliant thing that he did. So he did the following. So Nagata showed that R power G is actually is the following ring. Okay, so I need to describe some notation here. It is so this is what is, for those of you who know these terms, this is called symbolic Ries algebra. So I'll describe these notations in a minute. So where, this is where, so this T is just a placeholder. It's like a graded algebra where T is used to keep track of the degree. Okay, so where this is the brilliant thing that Nagata did, building on Zariski's idea. So is ideal of 16 general points in P2. So this is the ideal defining 16 general points of 16 general points in P2, and I power bracket M is actually what is called the symbolic power. And this is actually nothing but, so this is by definition, all polynomials. So of course, I is contained in 3-variable polynomial, right? So because that's the coordinate ring of the projective plane. So this is all polynomials such that F vanishes. So these points, let's say, are P1 through P16 up to order M, up to order at least M at P1 at each of. So this is the set of forms whose multiplicity at at each of the points is at least n. So this is really in symbols. Multiplicity of the zero locus of f is at least m for all I from 1 to 16. So that is this condition. So if you take that is called the symbolic power, which also has an algebraic definition using associated primes. I don't want to get into that right now, but geometrically this is what it is. So this is where, this is brilliant, because he thought of this action and connected this to this particular ideal of 16 general points. And now he proved this. So this is the first step. This is the first brilliant thing he did. Second important thing, which is more important for us, he also proved, okay, so basically he proved the following. If C is a degree D plane curve such that multiplicity of C at all of the points, so let me exactly write down, I don't want to get this wrong. So, okay, so let's see what he wrote. Multiplicity at all of the 16 points is greater than or equal to m. So let's see, sorry, so I thought I have written this down. So 1 second. If the multiplicity of all the points is at least m, then d by okay, so I should write probably, okay. Yeah, so d by m is greater than 4. Basically, this is specifically what he has done. So he has done this for r any square, but I'm taking r equal to 16. More generally, he proved that if r is square of s is a number greater than or equal to 4, integer greater than or equal to 4, and p1 through pr are general points.
So this multiplicity PIC greater than or equals to m?
M, yes, yeah, thank you. So if these are general points, and if C is a curve such that multiplicity of C at pi is greater than or equal to m for all I, in this condition, in this setup, we have degree of C divided by m is greater than root r. Okay, so I have written the r equal to 16 case here. And using this, okay, so this is the main theorem, and using this, it's not difficult to show. One can show that this ring is not finitely generated. Okay, this is not finitely generated, and hence it gives you a counter example to Hilbert's 14th problem. So this was, just as an aside, Nagata's main motivation, as I told you, is giving a counter example to Hilbert's 14th problem. Along the way, he proved this fundamental fact for points, either 16 points, 25 points, 36 points, and so on. So as an aside, at the end of the paper, Nagata conjectured he must have computed this for non-squares. So basically, take this to be star. Nagata conjecture is that star holds for all integers. Okay, so he proved it for squares, and that was enough for him. In fact, he just needed it for one specific number. He took 16, and that was enough for him. But he proved it, in fact, for 25, 36, 49, and so on. But he conjectured that this must be true for all integers, not just square integers. So this is a conjecture, and it is this can be stated in terms of Seshadri constants. So this is of course not the way Nagata would have stated this, but you can actually rewrite this statement and using the definition of Seshadri constant that I gave earlier. General points. So Nagata conjecture is stated. So the basic idea is that we have Seshadri constant is the ratio's degree by summation multiplicity, but all the multiplicities are m here. So this is r by m, and this is root r. So it will end up giving you this condition. Okay. So I will leave this calculation. So
excuse me.
Yeah.
Your first definition suggesting that Seshadri constant always will be rational number, but this one is showing the series.
Yeah, it does not correct. So there is a question that you can ask, but certainly we know that it in general will not be rational, right? Because all you know is that it's infimum of these rational numbers. In fact, this is a very good point that you raised. So these are rational numbers. Infimum may or may not be a rational number, but as you correctly pointed out, Nagata conjecture ensures that it is irrational.
Yes, that is interesting.
Yeah. So actually, that I have maybe 10 minutes more. So I'll just state this question that you raised basically. So let me just end this example remark on status of Nagata conjecture. So of course, Nagata proved it for all squares, as I said, but it is open if R is not a perfect square. So in particular, it is open for R equal to 10. So the first number so this is, I should add for R at least 10. Okay. So first number itself is open. So now this leads to the question. So I'll end with this. The question is, can Seshadri constants be irrational? So there are of course real numbers being the infimum of rational numbers. Can they be irrational? So this is an open question, and as of today, we don't know of any example of irrational Seshadri constants, but they are expected to be irrational. In fact, not just sometimes, but often. I'll simply write often. Okay, as one example is suggested here, right? Nagata conjecture, if somebody proves, then immediately you get irrational Seshadri constants. But often is something that I have to quantify, which I don't want to do right now. But let me just loosely speaking say that most of the time, Seshadri constants one expects to be irrational. But even so, we don't know of a single example. Okay, so let me just spend the remaining 5 minutes just giving. I just did this basic stuff today, but I want to highlight one recent result that we proved, which Nagata conjecture gives irrational Seshadri constant for R points. The question is, what about 1 point? Can that be irrational? So this is a joint work with. Okay, so can Seshadri constants be irrational for R equal to 1? So as you see here, Nagata conjecture only gives Seshadri constants irrational for R greater than equal to 10. What about R equal to 1? So this one can do. So this is joint work with Brian Harbone. So I will unfortunately not have time to sort of discuss the full setting. So let me just quickly state the statement or result. So before I state the result, this basic setup I'll give you. So let's say I blow up R points. So I take P2, I take R points in P2, I blow up in R points in P2. So I'm going to assume that. So the theorem is, so this is a joint work with Brian Harborn. The theorem says that if the following conjecture so let's see. Okay. So so let me just give you, call this XR. So blow up of R general points. I'll put general points here. So you have XR plus 1 and so on. So R can be any number, and you call the blow up of R general points by XR. If the following conjecture, so I'll write that conjecture after I state the theorem, holds for on XR minus 1, then there exists an F line bundle. In fact, it will be ample on XR such that epsilon and let's say a point X in XR such that epsilon XR LX is not a rational number. And what is this conjecture? So this is called either, for now I'll call this -1 curves conjecture, and I'll end with this. So -1 curves conjecture says the following. So X is a surface, projective, smooth, and so on. So quickly a definition. A curve, an irreducible and reduced curve C on X is called a -1 curve, or an exceptional curve of first kind, if C is a smooth rational curve with self-intersection -1. Okay. And then the conjecture is the following. If C, let X be as above, then if C is an irreducible and reduced curve such that its self-intersection is negative, then C is a -1 curve. So -1 curves are of course negative curves in this sense. But if you blow up general points, here I want to stress the point that these are general points. So this is important. Because if you blow up special points, you can construct -1, you can construct negative curves which are not -1 curves. But the conjecture is that this is an outstanding conjecture. No one, I mean, we don't know any proof. But it says that if you have a negative curve on a general blow up of P2, it must be a -1 curve. So this is a very strong conjecture, as one can show. If this, if XR satisfies this conjecture, then Nagata conjecture holds for R points. Remember, Nagata conjecture is a statement for R with respect to R. So if R point blow up has this very strong condition, then Nagata conjecture is true. So of course, this is a very strong conjecture. So assuming this conjecture, we prove that single point Seshadri constants can also be irrational. So of course, this is not a definitive result. As I told you somewhere, as of now, we don't know of any irrational Seshadri constant, whether it is 1 point, 2 point, 3 point, it doesn't matter. We don't know of any example. Nagata conjecture directly gives a multi-point Seshadri constant, which is irrational. But R is large here, at least 10. We prove that under a stronger conjecture. So because this stronger conjecture implies Nagata conjecture, we can get an irrational Seshadri constant for 1 point. Here the crucial thing is 1 point. Okay, so of course, as I said, this does not exhibit irrational Seshadri constant because we need that this conjecture should hold. Okay, so I was planning to say a few more things about some examples and proof of this, but I should stop now because it's already 2:50. Thank you very much.
Thank you very much for a nice talk. Are there any questions, comments, remarks?
Yeah, can you like give slight ideas? So how does this conjecture for XR minus 1 help to find such?
Yeah, so okay, so maybe I'll spend 2 minutes. So brief idea. Okay, so this gives me an opportunity to basically say general facts. So in general, if X is a surface and L is ample, if you have epsilon Lx is always less than or equal to square root L square, okay, always. Okay, so this is what we have. And moreover, so we have 2 facts. One is this, 2 is that if epsilon Lx is strictly less than L square, then epsilon Lx, there exists C such that epsilon Lx is actually is a Seshadri ratio. Seshadri constant is equal to Seshadri ratio, and hence this is a rational number. Okay, so this is the general facts. Okay, these are general and fairly easy facts. So in our case, assume Seshadri constant is rational. But that means that this must occur, right? If it is equal to square root L square, I mean, we'll also assume that because our goal is to only construct an ample line bundle with some property. So I'm going to first start with an ample line bundle, which has this property. Square root L square is not a perfect square. Then if the Seshadri constant is rational, it must be like this. So then hence is equal to L dot C by multiplicity. Okay, so C is in this case called, C is a Seshadri curve. C is a Seshadri curve. It achieves the Seshadri constant. Then this implies if you blow up the point, I'll just take 2 minutes. So if you blow up this point X, then C tilde square is actually less than 0. Okay, so you can show this. So it becomes a negative curve, and hence -1 curve's conjecture implies C tilde is a -1 curve. Okay, so
and
then
-1 conjecture for okay,
yeah.
okay, XR minus 1. Okay.
Yeah, actually, I think I made a mistake here. So thank you. Actually, I think if the conjecture holds for R plus 1. Yeah.
Yeah, that's what.
Yeah. Very good. Thank you so much. Yeah, it's not correct what I wrote. So you apply it for this. So this is XR. You blow up a further point. So this is XR plus 1. And then use some standard calculations, which of course you have to, I mean, it's not trivial. Give a contradiction. It's not trivial, but it can be done. Okay, so this is the crucial step.
So, Shrodna, are you done?
Any further questions?
Yeah. So could you explain some small application of Seshadri constant in number theory? or it has any application for classifying curves?
Classifying curves in the sense of so first question. See, the number theorists also study this. Unfortunately, I'm not completely familiar with this, so I cannot answer that question. I think the Seshadri constants have been looked at by number theorists, so I don't exactly know what the applications are.
Okay.
So that's the first question. Classifying curves, I'm not sure. I mean, you mean on a
Yes.
surface or something like that?
Yeah, over surface. So because it is associated with curves, so
Yeah.
it is a kind
No,
of
so
playing the role of invariant for a given curve. So by
yeah.
starting
So I'm not sure. So these Seshadri curves are special. So any curve which has this property is special in some sense, but I don't know if that can lead to any kind of classification statement.
Okay.
I think Saurav raised his hand. Can you unmute him? So who is the host?
You can
Hello?
unmute him.
Oh, okay.
Uh,
Can you hear me?
Yeah.
I just wanted to ask, can you give a hint why do you expect that there are many example where the Seshadri constant is irrational? Like if it is quickly.
You mean basically some kind of explanation for this sentence here?
Yeah.
Yeah. So I mean, it will probably not say much to you, but look at this statement that I wrote. So either Seshadri constant is equal to the square root of L square, or it is rational, right? Of course, this can also be rational, but we assume that L square is not a perfect square. Lots of times, most of the time, that's the case, right? L square is 2, for example, then this will not be a perfect square. So, but anytime there is a special, anytime this happens, the curve C seems to be a special curve. In fact, there can be at most finitely many curves like this. That's one theorem you can prove. So the Seshadri curves are finitely many. On your surface, there can be at most finitely many curves having this property. So it's expected that for most points, or more accurately, for a general point, this will not happen. So this will happen. I mean, the equality will happen. And then as soon as L square is not a perfect square, you have an irrational Seshadri constant. So it's not really an intuition, but this is special. Basically, that's, for example, what I wrote here. So negative self-intersection. So that kind of thing is special.
Okay, thank you.
I have one last question. It's also a bit vague in the sense, I mean, can we define Seshadri constant in the sense of Arakelov intersection theory? That is, you include a contribution at infinity comes to Green's currents or Green analytic cycle together with algebraic cycle. I mean, has this been studied?
Yeah, I see. So I don't know at all about this. So perhaps people have looked at it. So I'm not familiar with this at all. So, sorry.
Any further questions? There are no further questions. Let's thank the speaker again for his very nice talk.
Thank you.
So we reconvene in like 10 minutes at 3:10, right? Yeah, 3:10 for talk by Somnath.
Is Somnath present?
I don't see him. Not yet.
Hello, Somnath. Hello, Somnath.
Hello, hi.
Yeah, you are not there, and I don't have your phone number also. I was like thinking.
So I was there in the morning, and then I had to do some tests, like
Okay.
COVID test. So yeah, I actually I'll be traveling, so I had to do some COVID tests. So I had to go. So
Okay.
I missed some talks.
Hi, how are you? It's
Yeah,
Anil here.
nice. Yeah, Anil. Hi, good to see you.
So where are you now? Goa or in Kanpur?
No, I'm as such back in Kanpur. Yeah, but at the moment I'm in my home, so I'll go back this Sunday. So.
I see. Yeah, Rajnish was telling
Kanpur,
me
it
he
is
was
mandatory COVID test.
Yeah, UP, it seems to enter UP, it's mandatory. It's
Oh, I
irritating.
oh, wow.
Yeah.
So you done
Yeah.
with Goa or like?
Yeah, in fact, I have come back last year only. So,
I see.
well, I'm not sure it was Goa because, I mean, it was 2 months of Goa. Then ever since it has been at home, right? So, everyone is at their home. So, uh, so it was totally wasted in some sense.
Uh, yeah,
I mean, even
Rajnish was.
academic interaction was not possible. Yeah, Rajnish has joined there or something?
No, he refused, but he went to industry. But again, he wants to come back into academics again.
Yeah, I remember something like that was happening, but I'm not
Yeah.
sure what happened at the end.
Now is Prina back at the institute?
Yeah, so I suppose she's fine. She has a small baby, so she was on leave for some time, and after that, like I have not seen her. I mean, because even if we are in campus, we stay at home and all those
Yeah.
things, and she has to be careful with a small baby and so on. I suppose.
Now you're teaching online?
Sorry. Yeah, we
Are
are
you
teaching on
teaching online?
right. Yeah, last semester was a disaster in the sense I was teaching 1,200 students. It was a very big course.
Wow.
You alone
And
taught 1200.
No, I mean the linear algebra part.
But no, you tackled 1200 students. That's what I'm asking.
Yeah, so there are people for how do I say differential equations, a joint course, some differential equation and some.
Okay.
No,
but
then
you
you
have
should
TA,
not
that's what you
complain
mean.
then.
Sorry.
Surat, no, then you should not complain. Sumnata is teaching 1200 students, or we are teaching 120, and we are complaining.
Yeah.
No, I'm not complaining, but
No, we are complaining. We are telling you too much. There are many students. So,
no, I just meant like online teaching is a challenge, in that sense. We are all getting used to it. So it's very difficult.
And
Sometimes some
rampant copying.
sometimes, so since we are being recorded, I will not comment on
Oh, I
that.
see.
but
I forgot.
but the thing is, I mean, sometimes you take exam in some medium and then it just crashes. So
What do you use? Code Tantra or what do you use?
I think we sometimes use Code Tantra, sometimes use Great Scope. But for this scope, we used this course we used Great Scope.
I see. Yeah, we are teaching. I was seeing 160 or something, 160, and yeah, we have TS. Still, it's still a challenge.
Yeah, that's true.
The most difficult part is to find an exam paper which cannot be found online. And that's not it. Yeah, stop here.
Yeah. Yeah, and also, I mean, sometimes some student will have varied like internet connection, so evaluation also becomes difficult. I mean, what can you do, especially if you have a large course? After once you have like more than maybe 80, 90 students, it becomes very difficult.
Yeah. But 100 is astronomically huge.
Hmm.
That's huge. So, Shazam, you start?
Yes, we can start.
Yeah, I can start. Okay.
So yeah, maybe I just figure out how to share the screen. Uh, just a minute. What is happening? So is my screen visible?
Yes,
Yes.
yes, very much.
Okay, and is it full screen? I mean, yeah.
Yeah.
Yeah, we can
Okay.
see.
You can see. Okay. Great.
Okay, so let's start. So, welcome back everybody to the afternoon session, the second talk of the afternoon session. So from algebraic geometry, now we dwell a bit deeper into arithmetic geometry, and the speaker is Dr. Somnath Jha from IIT Kanpur. Oh, Somnath.
Okay. So yeah, thank you very much for giving me this opportunity. Indeed, it's an honor to speak in this event, and hopefully, future there will be more. How do I say? Offline event, and we can also meet and interact at SRM University. Okay, so so the organizers sort of told me to keep it slightly, broad-based talk. So maybe the experts, various experts, have to be a bit patient. So uh, so let me begin. So we begin with number field. So for example, we know this formula that we have 1 plus root minus 5 into 1 minus root minus 5 is 2 into 3. And if we view this in ring of integers of q root minus 5, then this shows that which is z root minus 5. So this shows that these are actually uh, that the unique factorization doesn't hold in z root minus 5. Okay, so z root minus 5 is not a UFD. So this leads to the notion that the world would have been much simpler if every for every number field, the ring of integers would have been a PID or equivalently an UFD. But it's not. So there is a notion to catch this failure, and that is called the ideal class group of a number field. So ideal class group of a number field measures how far away is the ring of integers from being a UFD. Okay. So or equivalently a PID. So let us see the formal definition. So you take a number field K. So by number field, I mean just a finite dimensional Q vector space, and it's a field extension of Q. So a fractional ideal in ring of integer, and OK is the ring of integer of the number field. So fractional ideal is a finitely generated OK submodule of K. So we are in the Noetherian setting, so I can just say it's a finitely generated OK submodule of K. And given a non-zero fractional ideal J, actually you can find that exists another non-zero fractional ideal I, such that I times J is OK. So and JK is the set of non-zero fractional ideals of OK. So they form an, one can see that they form an abelian group. Okay, and and it has a subgroup which is the set of all non-zero principal fractional ideals. So that forms a subgroup, and the quotient group is called the ideal class group. So JK mod IK, this is called the ideal class group of K. Okay. So one knows, I mean, although it's not essential, it can be proved using, for example, Minkowski theory, that this is a finite abelian group. Okay, so and as I said, this measures some kind of failure of the ring of integers to being a PID. I mean, of course, there are experts in algebraic geometry and so on in SRM. So this is also can be viewed as some kind of Picard group, but we don't need that for this talk. So this is an interesting object. So as I said, it would have been very nice if every ring was a unique factorization domain, and then every number field, and then ring of integer of a number field. Then probably Fermat's last theorem, for example, could have been proved very easily, and so on. So So for example, with this definition of class group, if you take the Gaussian integers, then the class group of that is trivial, whereas the example I started with q root minus 5, the class group is z mod 2z. So, but this this class group goes out of hand pretty quickly. The size of the class group and study of class group is difficult. So, for example, one of the seemingly innocuous question you can ask, does there exist infinitely many real quadratic fields, as simple as real quadratic field with trivial class group? Okay. So, for imaginary quadratic field, we know there are a list of 9 imaginary quadratic field. Goes back to work of Ignar, which has a trivial class group, but we can ask the same question that does there exist infinitely many real quadratic field with trivial class group? And the answer is not known. It is conjecturally, it is known that, I mean, it is conjectured that this should be yes, but the answer is not known. Okay, so it is difficult to study class groups. So it's a finite abelian group. So one of the way would be natural way to approach is you fix a prime p and study the p part for all prime p. I mean, you fix a prime p, you understand the p part. Then for all prime p, if you understand the p part, then by structure theorem of finite abelian group, hopefully you can understand the group. So that would be the approach we take here in this talk. But yeah, if there is any question till now, I mean, I've hardly said anything, but if there is any question now, we can take a very small break. If not, I'll move ahead. Yeah, okay, so okay, so maybe we continue. So we fix an odd integer prime p, and we take k to be a number field and in a natural number. So then, as I said, the idea is, let me repeat again. So it makes sense to understand the p part of the class group, because as I said, study of determining class group is difficult. So it's a finite abelian group. So you might like to fix a prime p and understand the p part of that class group. Okay. So so you fix an odd integer prime p. Odd will don't need at this stage, but at some point in the talk I'll need it. So just to be careful, I have put an odd here. So we fix an integer prime p and take k to be a number field and let n be a natural number. Then, so what I'm going to state a classical result on the estimate of growth of class group in a tower of number field. Okay, so as I said, we can take an increasing tower of number field and we can ask that how does the class group grow in that tower of number field? Okay, so this question Iwasawa was interested in, and the result I'm talking from is from 1959. So you take a number field k, call it k0, and you take a extension tower of number fields, k0 contained in k1, contained in kn, contained in k minus kn plus 1, tower of number fields, such that Galois group of kn over k. So each is a cyclic p to the power n degree extension. So Galois group of kn over k is z mod p to the power n z. I'll give, as you can think, it's not difficult to construct such example, and I'll talk about it shortly. But let's say that abstractly there is such extension of number field. Then what question Iwasawa was interested in, that how does the p part of the class group grow in such an extension? So, so this is the theorem of Iwasawa from 1959. So he says that let the power of p dividing the order of the class group, which is called class number, for kn is p to the power en. Okay. So we have kn and we have class group of kn, and that size is the class number. So and we are talking about p part of the class group. So suppose that has size exactly p to the power en. Then what can you say about en? That was the question. And excuse me, he came up with a nice formula that there exists constant lambda mu nu. So these are independent of n, but they do depend on p. So if I change p, then they become different, but we have fixed a p. So there are constant lambda mu nu in n, such that en. Okay, so en is lambda times n plus mu times p to the power n plus some nu. Okay, and this is for sufficiently large n, this formula holds. So the P part of the class group has order P to the power lambda times n plus mu times P to the power n plus nu, okay? For sufficiently large n. So this was the formula of growth of P part of the class group you also obtained for this kind of fields. So it looks so this particular factor is particularly sort of bad, and it gives an exponential growth. I mean, P power exponential growth. So one is interested in knowing at least is that growth is P power linear in P power. So is it P to the power lambda n plus nu, and whether this mu is equal to 0. So he also initially thought that that should be 0. This mu should be actually 0. But pretty quickly he himself came up with example that that is not true, and he came up with example of mu where this mu is positive. So, but let us now consider a special case of this kind of extension. So you fix a primitive p to the power nth root of unity. So a solution of like you consider x to the power p to the power n equal to 1. And you take a primitive p to the power nth root in q bar. So a solution which is not a root of any p to the power r for r strictly less than n. And then you adjoin it to q. Then this, if you adjoin it to q, then this q mu p to the power n plus 1. We know from our, let's say, first course in Galois theory that this group is isomorphic to z mod p to the power n plus 1 star units in z mod p to the power n plus 1. So, for example, Galois group of q mu p over q, you know, is z mod p minus 1, which is z mod z star. So, so in fact, if you take union over all n, then what you get will be the zp star, the units in the periodic integer zp, and inside that, then since periodic integer units, so since zp star is periodic integers times cyclic group order p minus 1, finite cyclic group order p minus 1. So inside that we can find an extension q cyclotomic, such that so we are denoting it by q cyclotomic. So such that Galois group of q cyclotomic over q is isomorphic to zp. So upshot of this, all this is that using p to the power nth root of unity, you can get a concrete extension of q, Galois extension of q, whose Galois group is the isomorphic to periodic integers. And since periodic integers have quotient of order p to the power n, we can in fact find inside this we can find sub-extension, finite sub-extension. So we can call it Qn, such that Galois group of Qn over Q is isomorphic to Z mod p to the power n. So this example is given here. Is actually has order Z mod p to the power n z. This is an example of this such kind of extension obtained by adjoining root of unity. Okay. So if you set, in fact, you take this q cyclotomic and you set k cyclotomic is k times q cyclotomic, then this Galois group of k cyclotomic over k is isomorphic to periodic integers. Okay, and then inside that, as I said, not only for q, you can find this kind of extension k subset of k and subset of k cyclotomic, so that Galois group of k n over k is isomorphic to Z mod p to the power n. So this was a general extension, any extension. Now I give a construction of a particular extension coming from this, what is called cyclotomic extension, obtained by adjoining p to the power nth root of unity. So now for this extension, you also said, okay, so he found example where mu is 0, non-zero, but he said, okay, if we restrict ourselves to cyclotomic extension, he believed still this will be 0. So he made a further conjecture, that refined conjecture or restricted conjecture, that okay, mu equal to 0 holds for k cyclotomic for any number field k. And this was one of the leading problem at that time. And first real breakthrough came from theorem of Larry Washington, who was also a student, and his student B. Ferrero in 1979 in the Annals of Maths paper. they proved that this mu equal to 0 is true, provided this k over q is abelian. So for abelian extension, they proved it. Essentially, they reduced it to, they used Kronecker-Weber theorem that every abelian extension is obtained by adjoining root of unity, and they basically restricted to proving this conjecture for q mu p to the power n. Okay, so and from that they could deduce it, and later, so John Coates' student Sinnott in 1984, in his Invent Math paper, gave a different proof using what is now called p-adical function. So using some p-adic measures and so on, he gave a different, completely different proof. So in any case, combining this thing, one knows that this mu equal to 0 holds if this k is an abelian number field. Okay? If Galois group of k over q is abelian. But till date, this remains open for a general number field. Okay? So if we take a k over q, which is not abelian, then this is wide open still. This conjecture of Lasser. So what can be done in the general case? So then in 2003, I think Coates and Sujata wrote a paper, and they suggested a completely different method of trying this, which is using abelian variety method to solve this problem about growth of class. So they suggested that this problem will be true if something happens to some arithmetic group associated with elliptic curve. So this is what I'm going to talk about in some sense today, I mean for the rest of the time. So they said there is some group, it's a Selma Group type group. In fact, they called it Feinstein Group. And if some property holds for this Feinstein Group, then this Iwasawa's mu equal to 0 conjecture, of course, in which there is no abelian variety involved, then this theorem will be true for a number field. Later, essentially the same result was kind of seen in a different way by Kumar Murthy and a Singaporean mathematician, Meng Fai Lim. Then this recent very strong mathematician, Konstantin Sesnavenius. So he also used a different abelian variety method, not elliptic curve, but a more general abelian variety, to again prove this mu equal to 0 conjecture. So general consensus seems to be that the only way for general number field is it can be done is to have some abelian variety method to attack this problem. Okay? And that is what going to be the topic of rest of my talk. So are there any question again at this point? This will be a good moment to take a pause. And so after this, we'll go to elliptic curve. Okay, so yeah, so I hope the setting is clear. So we have this Iwasawa's mu equal to 0 conjecture. So you take a number field and you attach p to the power nth root of unity, then you get a tower of extension. You fix a p and attach p to the power nth root of unity, then you get a tower of extension whose Galois group is z mod p to the power nz. And then how does the class group grow? So class group grows in p to the power, supposedly lambda times n, so linear in p to the p power for sufficiently large n. This is called Iwasawa's mu equal to 0 conjecture. And somewhat surprisingly, it seems that the way to do it is via abelian variety method, suggested first by Coates Sujata, then Sesnavenius, and also somewhat following Coates Sujata, but also
There is a question in the chat box.
oh, there's a question in the chat box. How to find the chat box? Okay, so 1 second, because I'm sharing this. Maybe where is Zoom?
So he's asking, is Iwasawa's theorem is on class group third bracket p or class group kn third bracket p to the power infinity? So p part of class group of kn or
p primary, yeah. So the answer is p primary. It is for all power of p. So if you look at the statement, I have not given p here. So I'm saying that it is the complete class group of kn. So cardinality of that. If p power n precisely divides that cardinality, that p to the power en, sorry, precisely divides the cardinality. So that could be the p part or p square part or p to the power 3 part or p to the power 4 part, anything. So this is p primary part, not just p torsion, p primary torsion. Are there other questions or this is the only question?
Thanks. This was the only question.
Okay, good. Okay, so maybe now we move to the second part of the talk, which is elliptic curve. So what is an elliptic curve? So the elliptic curve is a pair, and there is an algebraic geometric definition as smooth projective variety of genus 1 with a given point on it. But for this talk, maybe we can just think at more simply as solution of some cubic equation represented by some cubic equation y square equal to x cube plus ax plus b. But that is, it's a projective curve, it's oversimplification. So we can think it is a solution of the cubic equation with some point at infinity. If you want to make it precise, then you have to use a little bit of projective geometry. But it goes something like this. So here I have a picture. So this is a real locus. So these are to the locus of the curve, and this is maybe x-axis, and this may be y-axis, and you have 2 points. So sorry, this is the picture of the the locus of the elliptic curve on ER or something like that. But the interesting thing about elliptic curve is, given 2 points on the elliptic curve, you can add them. Okay, so roughly it goes like this. So you take 2 points P and Q and you join them by a straight line. Then it hits the curve at a third point. And again, you can make it precise using Bezos theorem and so on in projective geometry. But let's say all these good things happen. So it hits at a third point, and you can sort of take the reflection around the x-axis, and you can define P plus Q to be this reflection on the curve of the first point it hit. Okay? And this actually, so if you define P plus Q like this actually defines a group law. And well, put obviously not very precise and haven't defined everything, but the way P plus Q and Q plus P will be defined will be the same. So this defines an abelian group law on elliptic curve. So more generally, this is what is an abelian variety. So there is a group law on the points of the elliptic curve. If I take Q rational point or Q bar rational point or C rational points, so given 2 points, we can add them, we can get a third point. So there is a group law on the elliptic curve, and this group law is an abelian group law. And one of the first theorems, so for example, if you pick up Silverman book, one of the first theorem one comes across is called model-well theorem. It is due to actually model for Q, and then well proved it for more general number field. So you take K to be any number field, then Ek is a finitely generated abelian group. Okay. So that means, what does that mean? That just means that it means that K is isomorphic to some z to the power r, that is some finite abelian group. Finite abelian group. So, and more generally, you take E to be an elliptic curve over a number field K, then, sorry, not more generally, already I stated model-Wells theorem for number field. But so close related to this model-Well group is actually the way, so the way this theorem is proved is called weak model-Well theorem. So what one does, one actually proves in the literature, one proves that EQ mod something like 2EQ, or you can take any n, is finite. So this is called weak model-Well theorem, and then one uses some kind of height function to complete the proof. So, but this, in reality, you can never compute this group, EQ mod 2 times EQ. So what you can do, and how this finiteness is proved? This finiteness is proved using some actually basic Galois cohomology. So what one actually proves in the textbooks, if you see Silverman or Milne or any book you prefer, then one actually proves is n Selma group is finite. So, so already to prove this theorem, one comes across what is called Selma group. So let me define what is a Selma group. So a P Selma group of an elliptic curve. So again, once for all, I have fixed a prime P, and for safety, I have taken it to be odd, but this all holds for 2 also. So P Selma group of E over K is defined to be kernel of certain. So it's some kind of failure of global to local principle. So intuitively, you can think like we know for conic sections, Hasse principle holds, but for cubic equation, Hasse principle doesn't hold. So there is a famous example due to Selma that x cubed by 3 plus y cubed by 4 plus z cubed by 5. This has equal to 1 has solution over Q and over R and over every QP, but it has no solution. Sorry, it has solution over QP and R, but it has no solution over Q. So, so thinking about that, actually, Birch, I think, and they defined the Selma group. Castles defined Selma group, and he called it Selma group. So anyway, so this Selma group is some kind of failure of global to local principle. So you have some Galois cohomology, it's absolute Galois group of K. This acts on the P torsion point over K bar. And you have the restriction map. You have for every prime P, you have a decomposition subgroup. So Galois group of KV completion can be seen as a decomposition subgroup of this Galois group. And you have a restriction of Galois cohomology. Although it's Galois cohomology, these are called what is called crossed homomorphism. You can actually write them down. I don't really need it, so I haven't explained, but this can be easily explained. So this is this global to local kernel. It's called the Selma group, and as I said, there is an exact sequence. So there's an exact.
Can be explained?
Yeah.
I mean, of course, probably it is too technical. So
What this map? How is this map coming? Is that the question, Shratni?
Yeah, yeah.
Okay, so yeah, so this can be explained. I mean, so you have like let's stick to Q. Oh, what happened? So we have like we have GQ and you have like GQP. Okay, maybe P is there already. So QL. So Q is a subset of QL. I mean, the QL is the L-adic numbers. So by basic, how do I say? By basic class field theory or algebraic number theory, Galois group of QL, absolute Galois group of QL. So Galois group of QL bar over QL can be viewed as a subgroup of Galois group of Q bar over Q. And in fact, this is the decomposition subgroup. So this is the decomposition subgroup of this group. So you have a group and you have a subgroup. So you have this restriction map in Galois cohomology, and for every L, so you have a subgroup, and you have this restriction map to the. So this is called decomposite subgroup, but anyhow, it's a subgroup. So for every L, you have a subgroup of this group. So you have the restriction. And if you want to be precise, this is actually Q bar, and this is this is like QL bar. So on EPQ bar, so if you take Q bar and a P torsion point, then after the action of absolute Galois group Q, it will remain a P torsion point. So there is the action of this on this. So this module makes sense. And similarly, Galois group of QL acts on the QL bar torsion points of the elliptic curve. So there is this group also makes sense. So you have the restriction. So that's why I said it's some kind of
obstruction to lift.
Yes, so that's why I said it's some kind of failure of global to local principle, some kind of failure. And using principal homogeneous space, you can make it more precise. That this is actually a failure of global to local map. Okay, so yeah, the basic background idea is that for cubic curves, the Hasse principle doesn't hold. So global to local principle is not perfect. So we have a exact sequence like this. And this is how you prove actually in textbook model well theorem. Essentially, if you see, they may not say the word Selma group, but they embed it here and they prove actually this guy is finite. And even computationally, this is one of the main problem of elliptic curve, that you cannot compute the rank of the elliptic curve. You can never write a program to find the generators of this. All you can do is find the generators of this. But then you don't know whether it's coming from here or coming from here, where this is the SHA. This is called the Tate-Sheferovich group of E over K, which is again defined as a different but somewhat related failure of global to local principle. So the problem is we can only find a generator of Selma group. It is only this thing is computable. The generators of this is never computable. So we don't know whether it's coming from here or whether it's coming from here. That's why this algebraic part of the the elliptic curve theory, it looks simple, but it is never easy to work practically. Okay, so this is the P-Selma group, and as you can see, so this is a finitely generated abelian group. So if it's z to the power r, then this is a FP module, right? Finite field on P elements. This is a module over that finite dimensional FP vector space. So it has a rank, and this rank is this is inside this. So this rank, the FP dimension of this is the upper bound on the rank of the elliptic curve. So if it has Z rank R, then this will have FP rank at least R. Hence, FP rank of this is an upper bound on the rank of the elliptic curve. Okay. And in ideally, it should be. So this is one thing which is been very well explored by works of Manjul Bhargava, and on an average, they determine the rank of these things, and then we can say something about on an average the rank of this. And also there are a series of works of Mazar Rubin on different direction, on different viewpoint, but again, this rank of the P-Selma group, and they can say something about Hilbert's 10th problem and so on. There are a series of very deep and influential paper of Mazar Rubin also on this, exploring this kind of fact. And it is a conjecture, one of the fundamental conjecture, part of BSD conjecture, that this SHA, this other co-kernel, this guy is finite. Even if you consider not only P torsion point, you consider the whole of SHA, this itself is finite. And then the advantage of considering P infinity, you put together all P primary torsion. So here I define P Selma group. Similarly, I can define P square Selma group, P to the power 3 Selma group, P to the power 4 Selma group. And taking limit, I can define P infinity Selma group or P primary Selma group. The conjecture says that the P primary Selma group perfectly captures the rank of the elliptic curve. Okay. So this is part of the BSD conjecture, which is a clay problem. So anyhow, so this is some basic things about theory of elliptic curve, and I just have and Selma group. So I just have 8 minutes. How much time do I have? 8 minutes? Or
18 minutes, right? 18 minutes.
Oh, 18 minutes. Okay, so I have quite a bit of time. Okay, good. Okay, so now I'm going to talk about something related to now. So this was some basic thing about elliptic curve and Selma group, and now I'm going to link it to the previous thing I talked about, the class group. Okay, so what is the relation between class group and the Selma group? And that is what the title of the talk was, Find Selma group. So I'm going to introduce it now. But before that, again, we can take a small break. We have a bit of time, and if some question is there. So there should be some. There's some chat box. Yes. Okay. But this is already answered. Been answered. So, yeah. So are there any other questions? We can take a small pause, or we can move to the next part. Okay, so maybe not. So as I said, the summary of this part is that elliptic curve has a abelian group structure, and the Q rational points is an finitely generated abelian group structure. And if I take EQ mod P times EQ, then or EK mod P times EK, then it is subgroup of what is called the P-Selma group. And this is defined using some kind of failure of global to local principle, and this group is more computable. And similarly, taking put together all the P torsion point, P square torsion point, P to the power 3 torsion point, and so on, we can get P infinity Selma, which is just the limit of these groups. Okay, but we are interested in relating it to the class group, so we need to tweak this group a little bit. And the Selma group doesn't work that well, so what we need is a subgroup of this. Okay, so that is what is called Find Selma group. So this is defined as kernel of So before that, this P infinity Selma group I defined. So notice that as Surat. Oh, so here there is a mistake. The product over all. So yeah, I'm just trying to minimize noise. So So P infinity Selma group is defined. So here, as somebody asked the question, that it is H1 and then product over all prime L. But that all prime L is slightly difficult to handle. So what is more easy to handle is H1 of. So you take maximal algebraic extension. You take maximal algebraic extension Ks of K, and you take EP infinity, and then you take finitely many local factors here instead of all prime, which becomes more difficult to handle. So you represent the same group in a slightly different way using some basic things about Galois cohomology. So you don't take the absolute Galois group. You take the Galois group of Ks over K, where Ks over K is the Galois group of maximal abelian extension of K, which is unramified everywhere outside S. And S is a finite set of prime. So what is this finite set of primes? So you just need to consider primes of bad reduction of elliptic curve and the prime above P and the infinite places. Okay, so if you consider these three things, these three types of primes, then we need to just consider local condition over this primes. Okay, so what we did, we are just viewing Selma group in a equivalent other definition, where instead of all primes S, we have finitely many primes. All primes of K, we have finitely many primes of K. And what are those finitely many primes? It is any finite set which contains a set of bad primes, primes above P, and infinite primes. And in fact, since we have taken P is odd, then in an infinite prime also we can ignore. So, and instead of then GQ, the trade we have to do, instead of the whole Galois group, we have to take Galois group of Ks over K, where Ks is the maximal abelian extension unramified outside S. Okay, so this is then good to generalize to another definition of now what is called Feinstein group. So this is a subgroup of the Selma group. So this is defined as you keep the global thing as it is, but local thing instead of, say, so here we had the whole QV rational, QV bar, QL bar rational points of the elliptic curve. Instead that you only take P primary things here. So you have P primary things here, you have P primary things here also. So it's slight change, but it makes the group really small. Okay, so this is called the Feinstein group. And what is the relation with the Selma group? The relation is the following. So you have the Selma group, and you take for all V dividing P, so EQV tensor QP mod ZP. So it is the kernel of this. So it is a subgroup of the Selma group. Okay, so why this is important is not clear yet, but we'll come to it slowly. So at the moment we had the definition of Selma group, and we just took a subgroup of it. We tweaked the did not tweak the definition. We used the equivalent definition of the Selma group first, and then we tweaked it to get a subgroup of it, which is called the Feinstein group, and I am denoting it by RP infinity. Okay, and so I defined it over K, but this is not good for us because we want to relate it to class group. So what we'll do, so now you recall the tower that we have K subgroup of K and subgroup of K cyclotomic, and you take the Feinstein group over Kn, and then you take the limit, then you get the Feinstein group over K cyclotomic. Okay. So this is a discrete module. So so this is not so sorry. So this is a discrete module, so it is not so useful. So what we'll do, we take the Pontryagin dual of this, and since these are P primary discrete module, taking Pontryagin dual, it's enough to consider Hom with respect to continuous Hom with respect to QP mod ZP. So this Pontryagin dual then becomes a compact module, and what Coates and Sujata observed that or made a conjecture that this is a finitely generated ZP module. Okay. So this is also called mu equal to 0 conjecture. Okay, and that is the reason we talked about class group, and that is the relation will come very shortly. So we have this subgroup of the Selma group, which which we define to be Feinstein group, and the theorem of Coates and Sujata says that okay, you take this Feinstein group, P infinity Feinstein group, and you don't take it over K, you take it over K cyclotomic. So we have the cyclotomic tower discussed in the beginning, and you take the limit of this Feinstein group. Then this is a finitely generated ZP module. And this, so this is a conjecture. This is not known, of course, this is a conjecture. And why is it not known and what is the relevance? We are coming now. So saying this class group, the growth, where we have the growth formula that mu equal to 0 holds, and that this dual Feinstein group is a finite integrated ZP module, is essentially saying the same thing in terms of structure of them as modules over ZP power series T. Okay, so these guys, so we talked about class group of Kn, and this is the P primary part. So this is not P torsion. When I use this bracket, this means it's union of all P to the power n torsion. So this is the P primary part, and you take the inverse limit n. So this becomes a module over this. How, I don't explain, but I will say something about it. And on the other hand, this guy also is a module over this. And saying this is a finite integrated ZP module, and having that Iwasawa's conjecture that the growth of that the order of this is P to the power lambda n plus some constant for sufficient large n is saying that they have similar structure as module over this. Okay. So where is this ZP power series T coming from? So ZP power series T is a decent enough module. It's not a PID, but it's a two-dimensional complete Noetherian ring, and there is a structure theorem for such modules. This is called actually Iwasawa algebra. Okay, so this ZP power series T, power series ring in one variable over ZP. So this is a local ring with maximal ideal P, comma T. It's a regular local ring, so it's a UFD, and there is a structure theorem for modules over this. So you can do your characteristic element, you can do your linear algebra over this. It's not quite as good as PID. It's not an isomorphism, but you have to be satisfied with what is called pseudo isomorphism. But nonetheless, there is a structure theorem, and you can do some linear algebra or homological algebra. So why is this ZP power series T is coming? Because ZP power series T is actually this is a complete group ring. So you take ZP, it's a ring, and you take this Galois group of Kn over K, which is a cyclic group of order P to the power n. So then ordinary group ring with coefficient in the ring ZP of a finite cyclic group makes sense. And these are compatible. So you take inverse limit over this. So then what you get is a completed group ring. And this is actually the completed group ring of this extension, Galois group of K cyclotomic over K. Okay, so this is if you like, this is the definition, and one can show that this is isomorphic to ZP power series T. So that is how this is coming, and that is how this is related to this number field Galois group, and this is called Iwasawa algebra. Okay. So as I said, there is a structure theorem for finite integrated module over Iwasawa algebra, and that's why the structure, when we say that this is a finite integrated ZP module, or I am calling it mu equal to 0 conjecture, and the original mu equal to 0 conjecture of Iwasawa says that these two things have similar structure. So mu equal to 0 conjecture for this, and conjecture A for, so this I have called conjecture A, by the way. This conjecture A for this Feinstein group suggests that they have similar structure as ZPT modules. So now why these two are related is the following theorem of Coates and Sujata. So this was in 2003, I think. So K is a number field, and E be an elliptic curve defined over a number field K. And assume that this extension, so you attach, so P torsion point of elliptic curve, these are given by some algebraic numbers. So you attach K, these algebraic numbers, and you get an extension. So assume this is a P primary extension, meaning this is a Galois extension and Galois group is P primary. And this is slightly ambiguous in the sense by P primary, it can be trivial also. So it can be equal to K. Then also we are calling it P primary, slight abuse of notation. So then this mu equal to 0 holds for K cyclotomic. That means that those Kns, where Kn are coming from attaching P to the power nth root of unity, and Galois group of Kn over K has Galois group cyclic of order P to the power n, then this mu equal to 0 holds for this, if and only if this conjecture on this Feinstein group of the elliptic curve, this conjecture holds. So in some sense, this theorem prompted them to make this conjecture. Coates and Sujata. Okay. So first was this theorem that K is a number field, and then this mu equal to 0 conjecture holds for K cyclotomic. If and only if you have some statement over this elliptic curve. What is the statement? So take any elliptic curve and assume k EP over k is P primary. Then this is equivalent to having this Feinstein Group, the finitely generated ZQ model. So this is the formulation of this in terms of elliptic curve of this also equal to 0. So for example, as I said, this theorem of Coates and Sujata holds if you assume that this EP is a subset of K. So if K already contains EP, then this theorem will hold for an elliptic curve. I have 5 minutes, so maybe I skip the key idea of the proof. So key idea is you define such. I'll just say very briefly. So key idea is in a special case. So assume k equal to k contains EP, for example. So k equal to k of EP. Then you define a P Feinstein group, and using class field theory, because it contains EP, this H1 Galois homology becomes Hom. Okay, so H1 Galois homology, if the Galois group acts trivially, then the property of Galois homology is that this becomes a group of homomorphisms. And then using class field theory, you can relate it to S class group, this P Feinstein group, and relate it to S class group. Okay? And somehow that is the key idea of proving this theorem, and that prompted them to make this conjecture. So then, as I said, so there are works of Coates and Sujata on this, and recent work of Antonio Lai and Bharatwaj Palvanan. They wrote a couple of papers in this year and previous year on this, and then there are paper of Murthy, as I said, the paper of Murthy and the Singaporean mathematician. Then earlier work of Masima Kurihara and Christian Utrich, a student of Coates, and also my colleague Sudhanshu and Arivam Chandrakant in Mohali. So now, we are almost at the end, but now let me state some recent and not so recent result on this related to my work. But even before that, although you have 3 minutes, you can still pause for a moment, maybe if there is some question. Okay, then quickly I'll say some work on this. So today we talked about zeta function and so on in the morning talks at least. So for example, what Ramanujan observed is that congruence of two modular forms. Okay, so there is famous congruence of Ramanujan that delta q is congruent to sigma 11. So more precisely, so let's define delta q to be equal to this, and there is a congruence observed by Ramanujan between tau n and sigma 11n mod 691, and that is in modern algebraic number theory language. If you see, that is called congruence of modular form. Okay, so one is a cusp form and one is called Eisenstein series, and this is a congruence between them. So congruence of modular form basically all the way goes back to some classical work of Ramanujan. So then two modular form are said to be congruent if we want to define precisely if their residual Galois representation is so given a modular form due to work of Deline and so on. There's a Galois representation attached to it, and two modular form are said to be congruent if their Galois representation are congruent, or simply if you look at their Fourier expansion, their algebraic integers and their same mod p, then you call them congruent. And especially this kind of developed a lot by Hida, work of Hida. So in 2011, what we observed with Sujata in my thesis is that you take F and G to be two normalized cuspidal P ordinary P stabilized new forms. So basically two modular forms which are cusp forms and which are very good. So let's say they're new form. And there's some technicality of P stabilization coming from Hida theory. So assume that residual Galois representations are isomorphic. So their Fourier expansion are same mod P, let's say. Then we prove that this conjecture holds for one if and only if conjecture holds for another. So basically, this conjecture is made for all elliptic curves. So what we could do in my thesis 10 years back is that, okay, so you cannot prove it for one elliptic curve. Can you prove it for, if you know for one elliptic curve, can you do it for another elliptic curve? Or if you know for one modular form, can you do it for another modular form? The answer is yes, and that was one of the results we proved. And then later in 2012, I had some more result on this structure of this Feinstein Group over more general p-adic Lie extension. So there is a result of SER which says if you attach all p-torsion points of an elliptic curve, which is a non-CM, non-elliptic curve without complex multiplication, then there is a famous result due to SER, which says that this Galois group will be isomorphic to GL to ZP. So over such kind of extension, John Coates and so on has developed, starting with work of Michael Harris, what is called non-commutative Iwasawa theory. So in that setting, there are some further conjecture of Coates and Sujata on the structure of this Feinstein group, which I did not talk today, but I had some result on this structure of Feinstein group in 2012. So these are of course very old results, and this year we are revisiting these questions, and along with my colleague Sekhar in IIT Kanpur and our PhD students Sohan Ghosh, we have asked this question about function field. So the analog of Iwasawa's theorem in some cases are known in function field, and these questions make sense. So we have made some observation about structure of this Feinstein group over function field. And we are hoping this paper will be out in archive very soon. And yeah, so this is part of his thesis work, and he will be in job market very soon. So on goes. So with this, I end my talk. Thank you very much for your attention. And if there are any questions, I'll be happy to answer. Yeah, so there is already one question. So maybe I'll answer that first in chat box. I can see. So this I explained here. Maybe it went a bit quickly. So it is this relation. So yeah. So if you can see this, so this is the usual Selma group, and then here I have this is actually quite a huge group. So this EKV tensor QP mod ZP. Note that this is not any p torsion. This is the whole KV rational point of the elliptic curve. So it's like EQP. So there is a copy of ZP, and it tensor with QP mod ZP. So there is at least a copy of ZP. So this map to this map, you look at the kernel of this. So that is the Feinstein group. So it is usually quite small. And there is a relation, there are more cohomological interpretation of this group also, with what is so-called Iwasawa cohomology, but I didn't talk about it. But yeah, the difference between usual Selma and Feinstein is that Feinstein is a subgroup of it, and it is very small compared to the usual Selma group. So this group is quite huge, and it is the kernel from here to here. Does that answer the question? Okay.
Any further questions, comments, remarks? If not, let's thank Soma for his wonderful talk. And we reconvene for the next talk at 4:20.
For
Hello, I'm the next speaker, right? And in a few minutes.
Yes, actually a minute,
Okay,
yeah.
good. I got my
So
time
if I
right.
may, yeah. So if I may ask, how's your last name pronounced? Naiman or?
Naiman, yeah, perfectly. You
Naiman.
pronounced it right.
Oh, thank you.
Should I also share my screen?
Yeah, yes, please, yeah. That would be
You hear me fine, right? The
good.
sound is
Yes,
okay.
I do. Yes, it's all good. All's good. The screen's good, everything's good. Yeah. Actually, most people are there. Maybe I can. Sajad, can we start? Shall we start?
Yes.
Sajad, no? Yeah, okay. All right, so welcome back, everyone, for the last talk of the evening. The next speaker is Dr. Filip Naiman from University of Zagreb, Croatia, and the title of the talk is CQ curves of odd degree number fields and sporadic points. Dr. Naiman.
Okay, thank you very much, both for the introduction and also for inviting me to give a talk here. Okay, so what I'll be talking today is I'll be talking about two papers. The first one is joint with John Cremona from Warwick, and the other is a more recent one that I think appeared this week on Archive, and it's joint work with Abby Bourdon from Wake Forest. Okay, and first I'll define, as I saw that this is quite a diverse conference, I will try to define, well, most of the things I use, at least the non-standard ones. I will, of course, not define what elliptic curves are, such things, but in some specific things I will. So let E1 and E2 be elliptic curves. There will be a lot of isogenies here. So an isogeny from E1 to E2 is a surjective homomorphism with finite kernel. And we will say that an isogeny phi from E1 to E2 is defined over K if all three of E1, E2, and the map morphism phi itself are all defined over K. And if we just say an isogeny and no field is stated, then we will understand that this is defined over Q bar, not over the field of definition of the curves. So this phi also has to be defined for an isogeny to be defined over. Okay, and my talk, the main topic is Q curves, and an elliptic curve is called a Q curve if it is isogynous to all of its Galois conjugates. And just to emphasize this again, if we have an elliptic curve, a Q curve, which is defined over K, it does not mean that it's necessarily isogynous over K to its Galois conjugates. The isogenies themselves can again be defined over K. And well, the main topic I will talk about, torsion bounds and isogeny bounds for Q curves over number fields. So a more general setting for this, a more general notion is Galois representation attached to elliptic curves. So in particular, isogenies and torsion points are, in a certain sense, manifestations of Galois representation. So let me quickly define what Galois representations attached to elliptic curves are. So if E over K is an elliptic curve, K a number field, and P a prime, then we defined E of P to be the P torsion of E. So this is simply the subgroup of points defined over on the elliptic curve over K bar, which are the kernel of multiplication by P times R is equal to 0 in this group of elliptic. And of course, the absolute Galois group acts on this subgroup. And of course, if one has action of a group on another group or in general any set, and this of course induces a representation. And the induced representation here, which is called the rho EP, denoted by rho EP, from GK, the absolute Galois group, to GL2 of FP, which is the automorphism group of this object, which this is homomorphic as a group to Z times Z mod PZ squared. this is called the mod p Galois representation attached to it. And one of the most important topics in the theory of Galois representations of elliptic curves, the most important open problem is probably Serre's uniformity question or conjecture. It's well, it was originally formulated as a question by Serre himself. He didn't pose it as a conjecture, but it has been recently posed as a conjecture by both Sutherland and Divina after a huge amount of numerical data, which really supports that this conjecture is true. So, the question asks: does there exist absolute constant C such that for all primes P larger than C and for all elliptic curves E over Q without complex multiplication, that we have that the image of the Galois representation is as large as possible. So the mod p Galois representation is rejected. And the conjecture, as stated by I think both Sutherland and Divina, is that C equals 37 might be the best possible result, the truth. And so why look at Q curves? So there's, I would say, many reasons. For me, one of the most convincing is that the theory of Q curves is particularly beautiful and deep. But if you're not interested in Q curves themselves, they have been extensively really used in Diophantine equations, in particular in the so-called modular method to solving Fermat type equations, or generalizations of Fermat's last theorem. So, as in the proof of the Fermat's last theorem, it's really crucial to understand the Galois representation of the Frey curve that hypothetical solution produces, in particular the irreducibility of the Galois representation. So, in the same manner, it's important to understand the Galois representations of different Frey curves that arise in these general Fermat type equations, and these turn out to be Q curves. So here I will really just list some of the results proved using results about Galois representations of Q curves. So I think the first was to use this was Ellenberg in 2004, and later together with Bennett and Ng, they solved this equation here and this equation here using Q curves. And then there has been a number of equations that have been solved either completely or partial results have been obtained by Dulefet and Freitas, Bennett and Chen, Chen again, and Bennett, Chen, Damen, and Yazdan. So this list is by no means exhaustive. This is just a sample of results obtained using Q curves. And another theoretical result why I think one should care about Q curves is that Ribet showed in 1992, assuming Serre's conjecture, which was later proved by Carr and Vinton, is that Q curves are exactly the elliptic curves over number fields that are modular.
You said something about phase, that elliptic curve. So is that a Q curve? I mean, can you give some example?
Well, for these, so for these equations, the Frey curve that you produce is a Q curve.
Oh, that's what I'm asking. So
yeah.
Okay.
Yeah. So for each of these, the Frey curve will be a Q curve. So for the original Fermat's last theorem, you will get really an elliptic curve that is defined over Q. But here you will get a curve that is perhaps not defined over Q, but is defined over a number field, but it is defined over Q. It is a Q curve. So as you will see, I will say in a few slides later that Q curves are really generalizations of elliptic curves defined over Q. So I think this is a good way of thinking about them. They're, in a certain sense, the natural generalization of elliptic curves defined over.
Okay.
Yeah. Yeah. So Q curves are exactly the elliptic curves over number fields that are modular in the sense of being quotients of J1 of n for some n. This is the Jacobian of the modular curve x1 of n. And there are a few notions of modularity over Q, and a few notions of modularity, and they are all equal over Q. But over number fields, they differ. So Q curves are, in a sense, this, continue on what I said earlier, they're also, if you think about, elliptic curves a sensible generalization of elliptic curves over Q that they are modular in this sense. Okay, and I should also say, feel free to ask questions like this. I'm happy to answer any of them. So feel free to ask whenever. So which curves are Q curves? So we've had just a definition. So let's see some examples. So recall that Q curves are elliptic curves that are isogenous to their Galois. Well, if you take an elliptic curve defined over Q, then it's only Galois conjugate is the curve itself, and of course any elliptic curve is isogenous to itself. So any elliptic curve defined over Q will be again a Q curve. Moreover, a base change of a Q curve is a Q curve. So if you take an elliptic curve and use the same equation and define it over some other number field, then it will still be a Q curve. So the Galois conjugates will be just the curve itself. Also, if you take a twist, a quadratic or even non-quadratic twist of a Q curve, it will still remain a Q curve. So, so from this, you can also work out that if you take an elliptic curve with rational J invariant, it will still remain a Q curve. And a curve that is isogenous to a Q curve is still a Q curve. So this is, being a Q curve is an invariant of the isogeny class. And any elliptic curve with complex multiplication is also a Q curve. So if we take the set of E to be the set of all elliptic curves, then we can view, let's say, over Q bar. Then we can take the set of Q curves to be a natural set of this set of all elliptic curves. And then take another subset to be elliptic curves that are isogenous to an elliptic curve with rational J invariant, which then contains elliptic curves with rational J invariants, which then contains elliptic curves which are defined over.
Excuse me.
Yes.
Is there any elliptic curve over Q which is not Q curve? So it seems like
so over Q. Where what?
Over number field or number field.
Yeah, of course. Most elliptic curves are not Q curves. Over number. So over Q, I mean here, yeah, any elliptic curve defined over Q. But if you take any other number field, well, by any sensible measure, the 0% will be a Q curve. So Q curves really are over number fields that they are something that doesn't appear very often. It's a strange property. If you take an elliptic curve over a number field and you take its Galois conjugate, there is no reason for them to be isogeny.
Okay.
And this, I should say here, if you take, let's say, elliptic curves over Q bar, then really all of these sets are strict containments. So, yeah. All right, and Q curves also contain elliptic curves with complex multiplication, and they don't sit nicely in this tower of sets, so they will be viewed separately. And I gave short abbreviations to each of these sets. You see in the way I thought would be most natural. So QC are Q curves, IJ are elliptic curves isogenous to an elliptic curve with rational J invariant. J are elliptic curves with rational J invariants themselves, and B are base changes of elliptic curves over Q. And this, for at least the first part of my talk, the one which I talk about my paper with Cremona, this is, I would say, perhaps the most important tower of sets. And we will view, elliptic curves. We will view such elliptic curves either over a fixed number field or over all degree D number fields for some fixed D. And we want to prove, results about Galois representations of elliptic curves in each of these sets. So I really think, that it's important to understand Galois representations of elliptic curves in each step of the way. For example, if you want to solve these Feinstein equations, these Fermat type equation, then you're really interested in the Galois representations of elliptic curves that are here, that are Q curves. And a lot of statements, as you will see, will be true here, but will not be true. And in particular, the thing that's usually most interesting are degrees of isogenies and sizes of torsion groups in each and perhaps every one of these sets bounded. And, if yes, in what sense, by what are they bounded? And I should say that I will not talk about C. Their theory is kind of different, especially their theory in Galois representations, and it is in many sense different than non-CM elliptic curves here. And on one hand, and on the other hand, their Galois representations are now really well understood by papers of Bourdon and Clark and their collaborators. That they have a long series of papers, each very long, and also paper of Lozano or Robledo. So I can even say that we understand almost all we want to know about Clark's data. So, okay, let's view this set over we'll view them, this tower of sets of elliptic curves over Q and over quadratic fields and over cubic fields and over general number fields, general degree number fields. In particular, our results will be over general degree number fields, but let's see what happens over Q and over quadratic fields and cubic fields. So over Q, this set is not very interesting because all these are really the same over Q. And also, I should say, for each of these sets S, and for any integer d, we will denote by S of d the set of all such elliptic curves defined over all number fields of degree. And by P of S, I will denote the set of all possible torsion groups of elliptic curves in this set S. And obviously, you know, we saw that elliptic curves over Q over degree d, one number field are just curves over Q. So all of these are here. This is not interesting. And famously, by Mazur's torsion theorem, he showed that there's 15 possible torsion groups over Q. These are these groups, and here Cn denotes a torsion, a cyclic group of order n. And if we look over quadratic fields, then more interesting things start to happen. So if we look at possible torsion groups of all elliptic curves over all quadratic fields, then we get all these torsion groups. We get 26 groups, and this was proved by Kenko and Momos and Kamin. Kenko and Momos actually proved this, assuming a conjecture, which was later proved by Sheldon and Kamin. And I looked a while back at torsion groups of elliptic curves that are base changes of elliptic curves over Q. And we get all groups but 4. So we get 22 groups. And a PhD student of mine, and also even before him, Tortsakis, showed that torsion groups of elliptic curves, rational J invariance over quadratic fields, you get the same groups as here, plus one elliptic, one group, 13 torsion. So this was first proved by Tortsakis in his PhD thesis, but which was never published. And then my student Thomas Buljic proved this not just for 2, but for all primes. And I first got interested in this problem by looking at the question, what are the possible torsion groups of Q curves over quadratic fields? So you get 2 more groups, you get 14 torsion and 18 torsion. And so in particular, you get all the groups here apart from 1. You don't get 11 torsion. And I should say that all of these sets are complete in the sense that each of these torsion groups appears and the set being larger. So this is the truth. And also I should say that Lefort proved in 2013 that over any imaginary quadratic field, Serre's uniformity conjecture is true for curves if you restrict to curves which don't have, which are not isogenous to curves with rational J invariant and do not have C. So in particular, I think this is the only instance, only set of curves for which Serre's uniformity conjecture has been unconditional. This is quite interesting. We don't know how to prove Serre's uniformity conjecture over Q, but here, in a sense, if we look exactly here, we'll go over an imaginary quadratic field. And another interesting thing happens is that one can ask the inverse question. If we take a torsion, any of these torsion groups here, where exactly does it appear in this tower of sets? Does it appear anywhere or in some particular spot? And it happens that for some torsion groups, it does appear in some particular spot, which is perhaps very surprising a priori. We proved a while ago with Johan Bosman, Peter Brown, and Andre Duela that curves with 13 torsion are exactly here. So that they have rational J invariants, but they are not base changes of elliptic curves over Q. And similarly, curves with 18 torsion are Q curves, but are not here, so they appear exactly here. And curves with 16 torsion are exactly here. And for many values of n, one can also show that all curves with an n isogeny, and here this means a isogeny of order n, degree n, with finitely many explicitly stated exceptions are exactly here, proved by Peter Brown. And okay, let's go on to cubic fields. And a very recent result from last year is proved that torsion groups, what the possible torsion groups of elliptic curves over cubic. So we get this set of torsion groups. And if we look at torsion groups of base changes of elliptic curves, we get this smaller set. And as I said, Gurvit showed what the TJ of P is for all P. So in this case, we look at this set instead of this, we don't get any new groups. And one open problem, I think that is quite reachable in this, in this area is what are the possible torsion groups of Q curves over cubic field. Okay, and let's now go on to bounds over general number fields. So we saw what happens over degree 1 and 3, and as of course what happens for general D. And the most famous result is very famous result is by Merel, proved the so-called uniform boundless conjecture, because that the order of all groups in TE of D, so torsion of any elliptic curve over a degree D number field, any degree D number field is bounded by some constant depending only on D. So only on the degree, even though the elliptic curves changes and the number field changes, one only has finitely many possible torsion groups. And now you can ask after this, does it even make sense to look at these smaller sets? Because you can, is this best possible? And what we showed is that if you restrict these and if you look at smaller sets, you can do better. One can get uniform bounds. So together with Enrique Gonzalez Jimenez, we show that the order of groups in TB of D for D not divisible by any small prime is less or equal to 7 is 16, no matter what the D is, not being divisible by small primes. And if you look at just primes, so look at TJ of P, then this order of groups is bounded by 28. That's proved by Gurvit. And what we prove in our recent result is we push it a bit further, so we go to Q curves. We show that the order of groups in P, Q, C of P, so Q curves over any prime degree number field or any prime larger than 7, it is bounded absolutely by 6. And so we didn't do this for small primes, so it is done for 3, 5, 7. It's not yet. But if one includes also 2, 3, 5, and 7, then the correct bound is almost certainly 20. I would be very surprised if it's any larger, and certainly by this result it cannot be. Okay, and you can ask, well, can we do the same for all elliptic curves? Because here we restrict the degrees that we look at, and in Merel's result we don't. And the answer is it can be shown. I mean, it's not explicitly written out anywhere, but it's easy to see that no such bound can exist for torsion groups of elliptic curves over degree D number fields when D runs through any infinite set of positive integers. So no matter how carefully you choose your degrees, this set will become larger and larger and will never be bound. Really here that uniform boundedness really stops. This is kind of the best get reached in this sense. Okay, so what about isogeny bounds? So we still have our tower of sets, and we can define I of S to be the set of all possible cyclic isogeny degrees of elliptic curves in S. And here, one really doesn't have to make a difference between ij of d and ib of d, because twisting doesn't change the isogeny. So if the curve has an isogeny, then a quadratic twist also has the same degree isogeny. And here we know much less than about torsion, possible torsion groups. So we only know the possible isogeny degrees over Q. So this is the only degree the only degrees where all the possible isogeny degrees are known. So that's one thing, and also the only fixed number field where this is known. So there have been some recent results and some work to determining these results, at least conditionally, for some number fields, but nothing yet completely. And a while back, I proved. Did someone ask a question? In your recent result with Cremona, is there a specific reason for retreating into prime degree? Yes, I mean, we can't prove the results for general degree number fields. We could obtain some results over odd degree numbers. You will see soon. So our results will be everything that we prove with Cremona is over odd degree, basically. And there is really a reason for this, because Q curves over odd degree number fields, as I will say a bit later, they end up being kind of simpler than general Q curves over general degree. Okay, so the largest prime, so I proved a while back. I think no one really looked at isogeny bounds. So the only result that I know about general isogeny bounds is the largest prime. If you look at elliptic curves with in IJ, so isogenious to elliptic curves with rational J invariance over degree D number fields, if you throw out CM elliptic curves, and there really is a good reason to throw out CM here, because even over quadratic fields, and one single elliptic curve with complex multiplication can have infinitely many. If one does want some kind of sensible bound, and then you have to throw out curves for isogenies. For torsion, this is not. And it is bounded by 3D minus 1. And I also showed that it's bounded by D minus 1 if we assume a weaker version of Serre's uniformity conjecture. And this, motivated by this result, this weaker version of Serre's uniformity conjecture has been since proved by Lefun and Lemos. And this weaker version, so it says that, and what we know about Galar presentations, elliptic curves over Q now, is that either for large P, it's either the image of Galar is either surjective, so it's either GL2 of FP, or it's contained in the so-called in the normalize of the non-split Cartans. What they showed here is that it's either surjective or that it's equal to the normalize of the non-split Cartan. That it cannot be any subgroup, proper subgroup normalize of the non-split Cartan. And for this purpose, this is good. And this bound, I should say, D minus 1 is best possible. So this is really the truth. You cannot get any better. Okay, and yeah, so also related to the question, so the results that I stated were for prime degree, and I stated this result first because it is the cleanest result. But we also have results over any odd degree now. So let L be the possible prime degree isogenies of elliptic curves over Q. This is this set. So these are the of non-CM elliptic curves. So over, so you get these isogeny degrees over Q for non-CM elliptic. And what we show is that the primes, if you look at odd degree number fields and you look at Q curves, which are not CM, then over any odd degree number field, you will get exactly the same primes. You will never pick up any. And if D is not divisible by any of these primes, then not only is the largest prime 37, but really the largest possible degree of an isogeny, even composite degree will be still 37. And we even get bounds which are not absolute, but you get, even if you include CM elliptic curves for odd degree D number fields, you will get some absolute, not absolute, but constant depending only on the degree, not on the number field and not the curves themselves, but really only on the degree of the number. So this is in a sense kind of a Merrill's uniform, Merrill's theorem, at least for curves. Okay, so let me just say a few words about the ingredients that come into this and the theory behind. So one of the main results in the theory on which we improved a little bit is the result of Elkins from 1994, is that every non-CMQ curve over a number field K is K bar isogenous to an elliptic curve defined over a polyquadratic field. So hope this is clear what we mean. So you add a number of square roots to Q. And what we prove is every non-CMQ curve over a number field K is K isogenous to an elliptic curve defined over a polyquadratic field. Maybe I should say, maybe not really an elliptic curve defined over a polyquadratic field, but J invariant defined over a polyquadratic. So really the difference is very small. So here you have a bar, and here you have they should be really J invariant. But the important thing is here that really you can define this isogeny over K. So this is the crucial thing to proving our results, because this result wouldn't be really good enough. So this is really seems like a very minimal improvement, but it turns out to be crucial. And also, I should say, we really had to put effort. And this allows us to prove the following. If the isogeny class of a non-CM elliptic curve E contains an elliptic curve with J invariance J, at least an elliptic curve with J invariant, this should be on J invariant J, such that Q of J, so you join this J to Q, has no quadratic subfields, then E is isogenous to an elliptic curve E prime with rational J. So what does this mean? This really means that in our in this tower of sets, that Q curves over odd degree number fields are the same as elliptic curves. QC of D is the same as IJ. So this is the crucial thing. And a lot is known about Galois representations of elliptic curves over Q. So a lot has been proved. I've already said that what has been proved about towards series uniformity conjecture. And if you base change your elliptic curve, you really control the Galois representation. The Galois representation is perhaps some subgroup of index dividing D if you look over a degree D number. And if you twist, then you twist by a character. So this is really a minor change. And if you take an isogeny, we also know how to control what happens. So here really, while about over general Q curves and the general elliptic curves, we know almost really, I think it's safe to say almost nothing about their Galois representations. So almost some there are some very basic conjectures, in particular by Elkis, about Galois representations of Q curves, but nothing has been proved. And here a lot has been proved. So over odd degree number fields, these things become somehow this results of equaling these things over odd degree number fields, and these things really allows us to pull this in to set of curves that we use. And as I said, so here, this thing, maybe I should stress this a bit more. So if you have if you have a Q curve, if the isogeny class of a non-CM elliptic curve contains an elliptic curve with J invariance that Q of J has no quadratic subfields, then E is isogenous to an elliptic curve E prime with rational J invariance. So if you take a Q curve, and here it has to be this tells you if you look over an odd degree number. So it has to be isogenous to an elliptic curve with a J invariant defined in a polyquadratic. And since it's K isogenous, this J invariant has to be also defined in K. So it has to be defined both inside J invariant and the polyquadratic field. But since our number field K is of odd degree, and so you have a number field that sits both inside an odd degree number field and a polyquadratic field. So it has to be Q. So this is the only such number. So, and this tells us that basically what I said here. QC of D is just the same thing as IJ of D. And then Galois representations of such curves are comparatively well understood, and this allows us to obtain our results. And also, this allows us also to develop a quick algorithm to test whether given. So take an elliptic curve over some number field K, and we test whether it's a Q curve. So it works in the worst case by computing the K isogeny class. And this is also where this result comes in, because it tells you that just looking over in the K isogeny class, which is not so hard to compute, one can determine whether your curve is a Q curve or. But the previously known best algorithms in the worst case had to really compute the K prime isogeny class, where K prime is the Galois closure of K. I mean, imagine, so if K is of degree 6, you have to work over the degree 6 number field, and here, you know, the law group is S6, then you have to work over degree 720 numbers. You can basically do anything. Okay, so this was basically the presentation of my results with John Cremona. This is what we prove, and then so I gave it a talk at one conference where I gave a talk about curves over odd degree number fields, and then Abby Bourdon gave a talk about odd degree sporadic points on modular curves, and then we discussed this and saw that it would really be sensible to look at sporadic points coming from Q curves over. As I hope you will see soon, there really is a good reason for this, both odd degree number fields and even more over general number fields. So what are sporadic points? So we say that the point X of degree D on a curve X, capital X, is sporadic if there are only finitely many.
Excuse me. Sorry.
Yes.
Could you go back to your previous slide?
Yeah.
Yeah, here you mentioned that there are Galois representation of curves in IZDs are comparatively well understood. What do you mean by this? Means.
So, for example, we can bound if you take the mod P isogeny, the mod P Galois representation, and you give a D. So I can give you a bound on the, let's say, index in GL2 of FP of an elliptic curve, for example.
Here D is odd, always.
Yeah. Well, IJ of D for any D. This statement is true for D is odd, but IJ of D is understood for, I would say, for any D.
Okay. Okay. Thank you.
Really, the odd degree really comes into bridging this, having this E. So these things are comparatively well understood for any D, and over odd degree we have this equality.
Okay.
Thank you. Okay. So in a sense, a sporadic point is a point of degree of smaller than you would expect. So elliptic curves have not just curves. Algebraic curves have points that arise for some geometric reason. For example, if you have a degree 2 map, if you have a hyperelliptic curve, you have y squares equal f of x. Then this curve obviously has infinitely many quadratic points. You can take your x to be any rational number, and then y will be at most quadratic. So you'll have infinitely many quadratic points. For a hyperelliptic curve of genus 2 or more, a sporadic point would be a rational point, because there's no particular reason why a hyperelliptic curve would have a rational. And you know that by Falting's theorem that there would be only finite. So this means sporadic. I should say also that there's a few definitions of sporadic. They have the kind of the same spirit, but some, you know, say kind of different. Some will say that that it's a point of degree d which is smaller than the smallest map to P1. So if you have a degree 2 map to P1, let's say like hyperelliptic curve, then this produces an infinite many degree d points. But we use this. This is both. I think the easiest to state, and at least I think it's fine enough. Okay, and I should also say, so I mentioned torsion groups of elliptic curves over degree d number fields and isogenies over degree d number fields of elliptic curves. So really the difficult thing. So how does one do this? So one really has to find points on the corresponding modular curves. So here one finds the modular curves x1 of n of degree d, and here next x naught of n of degree d. And it's usually kind of easy. I shouldn't say very easy, but easier. The easier part is to find for which modular curves there are infinite. The really hard part is finding what the you know, sporadic points on these modular curves are, and I will call this the sporadic groups. These are those that appear finitely many times, in the sense of there's finitely many elliptic curves with these torsion groups and isogenies over the. This is really the hardest. So, for example, the groups that appear infinitely often in T of D are known for D up to 6, and D equals 3 was proved by Kim and Schweizer, D equals 4 by Kim and Park, and D equals 5 and 6 by Derricks and Sutherland. And the sporadic groups, here I don't, again, these are just corresponding to sporadic points in the modular curves, not the sporadic groups in the sense of classification of finite groups. The sporadic groups in P of D are known. And the degrees that appear infinitely often in I of E of D are known for only D equals 2, D equals, and a recent result D equals 3, beyond in 2001, while the sporadic ones are known only for D equals. Again, here you can see both. We know more about the degrees that you know the points that are not sporadic than the ones that are. Also, we know more about torsion groups than about isogeny. And so one can ask, should one expect, you know, a lot of, if you would take the modular curve x1 of n and take n to run through all values, should you expect sporadic points or not? And the answer is that you should. So for large n and large degrees, there is really an abundance of TM sporadic. So in particular, Clark, Genau, Pollack, and Saya proved in 2019 that for all n larger than 721, the curve x1 of n has a sporadic. And a recent result of Bourdon, Eider, Aliu, Odomodu, Irai showed that if E is a CM elliptic curve, then E corresponds to a sporadic point on x1 of n for infinitely many n. So a single point can really produce sporadic points, but just on different curves. Really, CM, there really is a tight connection between sporadic points on the modular curves x1 of n and elliptic curves of contact. So every CMJ invariant is a so-called sporadic J. And they also proved that assuming series uniformity conjecture, there are only finitely many rational J invariants giving rise to a sporadic point in the union of all x1 of n. I should say non-CM, many rational non-CMJ invariants giving rise to sporadic. And the set of sporadic J invariants in Q contains these two J invariants. So this set is not empty. And also all CMJ. Oh no, I'm sorry. Here you don't have to really support non-CM J invariants. There's only finitely many rational J invariants. It's these two values and also all CM J invariants and perhaps a few more. So there's finitely many J invariants, but not finitely many sporadic. And they also proved that if you have a point x on x1 of n, which has a degree which is very small compared to the index of modular group gamma 1 of n in PCL2 of z, then x is sporadic for any positive integer d and any point y on x1 of d of n with dy of equals x, where the point y is sporadic and where p denotes the national map from x1 of d n. So in a sense, this if the degree is very small, then it lifts to a sporadic point on infinite many of these modular curves. And something I proved almost 10 years ago, the elliptic curve E, this one, with rational J invariant, with this J invariant here, which is in element BB label 162.3, has a point of order 21 over its cubic field. It has a point of order 21, while the modular curve x1 of 21 is fine with many points of degree up to. So this really gives a sporadic point on x1. And this is also the least degree of a sporadic point on x of n for any value n. And also there exists a positive finite number of elliptic curves up to q bar isomorphism with an isogenic over q for these values of n. So the lowest degree of a sporadic point on x naught of n is 1. So all of these really give you, there are sporadic points on x naught of n for all of these. And recently, Bourdon, Giller, Rouse, and Watson proved that this J invariant here is the unique non-CM rational J invariant, giving rise to a sporadic point of odd degree on x1 of n. And Van Hooy has a huge list of sporadic points, a database where he computes a bunch of sporadic points on x1 of n for all n up to 80. There are no sporadic points of degree 1 or 2 on x1 of n, while there exist sporadic points of degree 3 and degree d for all p from all d between 5 and so I think it's a very interesting open question. Are there any sporadic points on x1 of n of degree 4, or more generally on the modular curves x1 of n? So this is an open question, and it might be easily that degree 4 is the largest degree such that there is a sporadic that there is no sporadic point. And we saw also that for large D that there's always a sporadic with D. Okay, so why should we care about the sporadic points? I think the most convincing reason, at least for me, is the relationship with series conformity conjecture, which I said is I guess the most notable problem in this. So in this paper, we proved that suppose that all non-CMQ curves corresponding to sporadic points on x1 of p squared lie in finitely many isogenic classes as p varies through all primes. Well, then series uniformity conjecture holds. So the finiteness of sporadic points corresponding to Q curves on just these modular curves would prove series. And I think I'm quite short on time. Actually, I should be finishing soon, so I will just I will skip the proof of this. Yeah, I will skip. So in a sense, we prove that if we would have something that each non-surjective, so each elliptic curve with a mod p representation would give a sporadic point. So if we prove the finiteness of sporadic points, we prove the finiteness of those values, which then proves that that there is an absolute bound, which is what exactly on the non-surjective primes, which is exactly what there's an uniformity conjecture asks. And also, basically, the same argument also proves the same result if we take, instead of x1 of p squared, we take x of p. So one can also prove that there are finitely many sporadic non-CM points on x of p corresponding to elliptic curves defined over q as p varies through all primes. and then Serzian from conjecture holds. And here, if we look at these modular curves, then we can look at elliptic curves defined over Q. While here we look at these modular curves, x1 of p squared, and we have to look at curves. Good reason why to look at sporadic ones on Q curve. And of course, this motivates the question: does there exist only finitely many isogenic classes of non-CMQ curves which give rise to sporadic? For example, and if yes, this would imply Serzian form texture. And the main result of our paper is that we prove this for odd degree values. All the odd degree sporadic points on x1 of n correspond to non-CMQ curves, corresponding to non-CMQ curves lying the isogenic classes of this J invariant that we solved. And also, if P is a prime, if X is a point on K, a sporadic point of odd degree corresponding to G curve, and E has Cn. We prove a few other results, but lack of time, I will just skip them. I don't want to go over time for the last talk, so I will end here. And yeah, thanks for your attention.
Thanks for the nice talk. Any questions, comments, remarks? There are no further questions. Let's thank the speaker again, and also all the speakers of today's afternoon for the nice talks.
Yeah.
So yes, I guess we meet again tomorrow morning.
Tomorrow at 10.
Yeah. Yeah, now you can close, I think. So,
Okay, sir.
yeah.